The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome. My name is Sally Liorno. I am a staff engineer at Stryker Orthopaedics and a member of the ORS Industry Engagement Committee. I will be the moderator of today's webinar. Thank you for joining us for today's webinar, New Concepts of the Interaction of Corrosion, Tribology, and Biology in Orthopedic Implants, sponsored by the ORS Industry Engagement Committee. Please note that Stryker Orthopaedics is not a sponsor of this webinar. In addition, any comments and opinions expressed herein are solely those of the individuals involved in this webinar and do not constitute official statements or positions on behalf of Stryker Orthopaedics. As I mentioned previously, this webinar is sponsored by the ORS Industry Engagement Committee. This committee is dedicated to providing the exchange of information that is of mutual interest to the Orthopedic Research Society membership, its board of directors, and the orthopedic industry. In addition to providing webinars such as the one you are about to hear, the committee organizes several sessions at each year's annual meeting dedicated to this purpose. Please see the program book to learn more about the sessions to be hosted by the committee throughout the 2016 annual meeting. Please be aware that this webinar is also being recorded and will be posted on the web. All webinar participants will be muted during the presentation. If you have any questions, please type them into the questions box in the menu located on the right side of your screen. We will address the questions at the end of the presentation. In today's webinar, we have a wonderful speaker from Syracuse University, Dr. Jeremy Gilbert. Dr. Gilbert is a professor of biomaterials in the Department of Biomedical and Chemical Engineering in the L.C. Smith College of Engineering and Computer Science at Syracuse University. He is currently editor-in-chief of the Journal of Biomedical Materials Research, Part B, Applied Biomaterials, and past president of the Society for Biomaterials. Dr. Gilbert was elected as a fellow of the American Institute for Medical and Biological Engineers in 2004 and was inducted in 2012 as a fellow of the International Union and Societies of Biomaterial Science and Engineering. He is the founder of the Syracuse Biomaterials Institute at Syracuse University and was appointed in 2013 to the Medical Devices Committee of the Food and Drug Administration. Dr. Gilbert has published over 160 peer-reviewed manuscripts or book chapters, 230 conference transactions, and 10 patents. Dr. Gilbert's research interests involve the study of biomaterial science with emphasis on the electrochemical behavior of medical alloys and their interaction with the biological systems, implant retrieval analysis, the role of reduction reactions on biocompatibility, the mechanical electrochemical interactions at metal oxide solution interfaces, and the development of novel mechanical, electrochemical, and polymeric test methodologies for orthopedic, spinal, dental, cardiovascular, and ophthalmic medical devices and biomaterials. Thank you for joining us, Dr. Gilbert.
Thank you, Sally. I want to extend my thanks to ORS and the Industry Engagement Committee for the invitation to speak here today. I do appreciate the opportunity, and hopefully all of our participants will learn something new from my presentation. So as the title indicates, I'd like to speak today about new concepts of the interaction of corrosion, tribology, and biology in orthopedic implants. And before I get going, I do want to disclose that I received research funding through Syracuse University from DePuy Synthes and Stryker Orthopaedics. I am also a consultant to DePuy, Stryker, Zimmer Biomet, Medtronic, and Corin. And as was indicated, I'm editor-in-chief of the Journal of Biomedical Materials Research, Part B. So in today's presentation, I'd like to focus on a number of topic areas that I think we've seen some significant advances in the last couple of years, focused around the concept of mechanically assisted corrosion, which can occur primarily in modular tapers being the major concern these days, but also anywhere where you have the potential for mechanical factors to disrupt the surface of these medical alloys that we use in orthopedics. As part of this presentation, I'll talk a little bit about the basics of corrosion, the fact that corrosion is not just about oxidation, particles, and ions, but also includes the reduction half-cell reaction and the consequences of that. Also to discuss oxide films and the nature of their growth, which is a high electric field growth model. I want to talk about what happens when oxides are disrupted and they subsequently repassivate, and to look at them in the context of fretting corrosion and to bring some engineering analysis tools to better understand the relationship between abrasion and repassivation. Then I'm going to shift gears a little bit and talk about the interaction of these metal surfaces with the biological system, focused on how reduction reactions influence cells cultured on metal surfaces. And then finally to talk a little bit about how inflammatory processes, and in particular respiratory burst and reactive oxygen species, may affect corrosion, and some of our documented evidence of cell-induced corrosion, inflammatory cell-induced corrosion in retrieved implants. And hopefully by the end I will present to you the idea of this new paradigm in understanding interactions of metal alloys with the biological system. That is, that corrosion causes biology, but biology also causes corrosion. So as we all know, metallic biomaterials in orthopedics are primarily the three principal alloy systems of titanium, cobalt, chromium, and stainless steel. However, there are these other alloys, zirconium, tantalum, tungsten, niobium, etc., that all have oxide films on their surfaces. These are called passive oxide films, and I give you some examples here of titanium and chromium oxides, but really they are not passive. And when we use the word passive, what we are referring to is they act as a kinetic barrier. They slow the rate of reactions that would normally go on in the absence of the oxide, but because that oxide spontaneously forms, it slows those reactions down. And I'm emphasizing this because really these passive films are quite dynamic. They tend to change their chemistry and morphology and thickness with conditions like the voltage across the interface and what solution they are immersed in. So these are important concepts to understand. Why are they important? Well, in corrosion in vivo, and I've shown this slide I think now for many years, we've known about the nature of corrosion of these medical alloys going back to the late 1980s, when in 1988, Svensson et al. Showed pseudotumors forming from a cobalt-chromium modular taper junction. We also know that all of the currently used combinations of alloys are susceptible to this concept of mechanically assisted corrosion. The titanium, cobalt, and stainless steel-based alloys all have this oxide film, and as a result, they are susceptible to the disruption and subsequent repassivation reactions that can go on. Additionally, we've been able to model and mimic much of the mechanically assisted corrosion process in the laboratory in relatively simple tests like this one that we published in 2009, but has its precursors going back to 1994, where we can apply cyclic loads to the head of a femoral component and monitor both the voltage of that component as well as current that would be generated from the fretting corrosion passing through to a second electrode. We've noted that these currents will rise with the increase of the cyclic loading, and that the overall voltage of the system can become more negative as a result of the abrasive and repassivating processes. But also, it's important to think about the mechanics of the modular taper junction, and this image here is a simple engineering analysis, mechanics analysis of the frictional interactions that go on during impaction of a head on a neck. And you can see that when you drive the taper into the head, the trunnion into the head, that you develop a pressure and friction. And those frictional and pressure effects remain to work against one another to hold that, to lock that taper in place. When you try to extract the taper, then the friction switches to the opposite side, the pressure is acting to pull out, and it actually comes out at a lower force than the force you use to impact it. And in fact, that ratio of extraction to impaction force is roughly about 0.5 to 0.6 for typical conditions of a modular taper. The graphs I'm showing here show how that ratio of extraction to impaction varies with things like the taper angle as well as the coefficient of friction. And importantly, you can see that when your coefficient of friction of the engagement drops well below 0.2, that your ratio falls away quite rapidly. And so if you have contamination or other factors that are reducing the coefficient of friction at that junction, then you can see a loosening of that component relatively easily. In addition, we've recently been investigating how the mechanics of seating may influence the properties and the fretting corrosion reactions at the taper interface. One such test is the seating mechanics test shown here. What we do is we basically apply a sort of a quasi-static ramp loading to the head, while also monitoring with two non-contact displacement sensors the relative motion of the head to the neck. And shown are two graphs, one where we're seating only to 100 newtons of load, and another one where we're seating to that should be 4,000, not 40,000, apologies there, 4,000 newtons of load. And what you can see in these plots is that the head sits down onto the taper. In the case of 4,000 newtons, that's roughly a 250 micron seating displacement. And with 100 newtons, you only get maybe 40 microns of seating displacement. So these curves represent the nature of the engagement mechanism between the tapers. And there are elements of it that are important, including the area inside the curve, which is essentially the work done to seat that head. And also the slope of the loading line, which is essentially a stiffness-like measurement that is a function of the materials used, the nature of the interface, the friction, and so on. And I'll show you that in a minute. So one concept that comes out of understanding these seating mechanics is the concept of taper compliance or stiffness. And that is that when you drive a head onto a neck, there's microtopography, there's modulus, there's a number of factors that influence how stiff that system is. And in this example, I'm showing a stiffness parameter K for a thin annular ring that's being pushed down onto a rigid trunnion. And so the equation for that engagement or that stiffness has the modulus of the ring, features of the geometry of that ring, the taper angle, the coefficient of friction. So all of those go into this parameter, this slope parameter, that is measured when you seat the head onto the neck. And I believe that this compliance has a very important role to play in the overall seating mechanics of modular tapers. Now, once we've seated heads, we can go ahead and test them. And there are a variety of test protocols, I think, that are in development, but really ones that are going back to things that we did in the early 90s. This one particular test called an incremental cyclic fretting corrosion test is one that helps to do assessment of materials or designs or local geometry effects on the fretting corrosion of these modular junctions by applying a cyclic load, 3 hertz, 3-minute intervals in phosphate buffer with the sample held at -50 millivolts and going from 100 newtons to 4,000 newtons incrementally and measuring the response both in terms of the electrochemistry as well as the motion of the head onto the neck. And this is work that we've just recently had accepted for publication, will be coming out in 2016. So in terms of the head motion, what we see in these relatively short-term, about an hour-and-a-half tests, indicate how the head moves on the neck. And because we have a sensor that's on the superior side and the inferior side, we can get some assessment of the rocking and toggling that might occur. And in this example, for instance, the DVRT1 is a superior sensor, DVRT2 is a inferior sensor about that head-neck junction. And you can see initially the head appears to rotate, that is, rocks upward on the superior side and then seats downward, while the inferior sensor just shows a progressive seating of about 50 microns. And so this is showing you the motion, which is schematically demonstrated in that little cartoon there, driving that implant, the head, into the trunnion. Now, simultaneously, we can capture the currents that are generated by the fretting corrosion mechanism at the junction, and we can look at them as a function of the cyclic load magnitude, this curve on the right, or just plot it out over time, capturing 1 second or 1.5 seconds of data periodically throughout the entire course of the test, and that's what this left-hand plot is showing. And so you can see there are spike transients when we change the magnitude of the cyclic load, average or mean current levels that rise as we increase that load, and there is a load at which the fretting currents begin to occur. And so we can look at that onset load, we can measure the current at the maximum cyclic load that we apply, and so these are measures of sort of the performance of that modular taper that can be used to assess materials, assembly, other surgical issues, and the factors that might impact on modular tapers. So generally, implant modularity and its study relies on understanding the mechanics of that interface as well as the electrochemistry. And so I've talked a little bit about the mechanics, and let me now move to a more general discussion of corrosion and electrochemistry. So in this slide, I am trying to convey the fact that corrosion has both oxidation and reduction reactions that are present. And just schematically, I'm showing a metal surface with oxide film on that surface. The oxidation reactions might be metal going to metal ion, but also metal and water reacting to form metal oxide and releasing hydrogen ions into the solution. When these reactions occur, they both, you can see, generate electrons that stay in the metal, and they will go to where reduction reactions happen. These reduction reactions might be right next to where the oxidation is taking place, or in the case of, for instance, spreading corrosion in a modular taper, the reduction reactions will likely occur somewhere outside of that taper or at the mouth of the taper and are distributed over that surface. These reduction reactions take these built-up electrons in the metal surface and reacts them away. Typically, we think of oxygen and water and electrons forming hydroxide ions, but it's also important to note that there are these reactive intermediates that can arise that include hydrogen peroxide, hydroxide radicals, hydroperoxyl radicals, and oxygen superanion. All of these show up in small quantities as a byproduct of this reduction reaction, and these, it turns out, can have some very profound effects. Indeed, they are very similar to molecules generated by the inflammatory system to fight infection. And so the consequence of these molecules on the biological system will be discussed in a little while. But you'll notice that the positive ions create a positive current out into the solution, and then the cathodic currents create an equal and opposite current. And so while there are currents flowing, typically without an external source, these all happen on the single implant surface. And again, when you think about this in the context of currents, the metal is oxidizing, the oxygen is reducing, and because they have to balance out on average, you wind up at a curve that is defines the corrosion current and the open circuit potential for that system, where these two lines that intersect at this point are given by this Butler-Volmer equation. Now, this representation of the relationship between the anodic and cathodic currents is only for the case where there is no oxide films. And it's important to note that these currents rise by factors of 10, they're exponential essentially, with the voltage. So voltage shifts away from open circuit can raise the net current by orders of magnitude as it moves either positively or negatively in an electrochemical reaction. So this link between chemical reactions, releasing ions, as well as currents that flow is an important one to understand in corrosion. When you have a passive alloy present, the oxide film shows up at certain voltages, not at all voltages, but at certain voltages, and will passivate that surface and reduce that active corrosion. So in that prior picture, the active curve might have been this line continuing out, but at this passivating potential, oxide film begins to form and covers that surface and makes the currents much less than they would be in the absence of it. In some alloys, like stainless steel and cobalt chromium, there's another potential, the breakdown or transpassive potential, depending on the alloy, where you begin to get a runaway, essentially a loss of the passivity of the oxide film, and either pitting corrosion or a generalized corrosion attack of that surface. When you superimpose the reduction reactions on that curve, this black line is the representation of what you would measure in a simple polarization test. Now, I want to move to talk about oxide films a little bit. They are fairly complicated materials. I might, if we just had discovered oxide films in the last 5 years, they probably would have been called smart, self-healing nanobiomaterials because they are smart, they respond to stimulus, they are self-healing because they reform once they're disrupted or abraded. They're nano because those oxides are only a few nanometers thick, and they're biomaterials because they're the material that is exposed to the biological fluid. But what happens in that few nanometers of oxide is very important. First of all, there is a very high electric field that is generated because of the passive semiconducting nature of this oxide. Metal ions want to react from the metal, and they build up along this interface, and then electrons tunnel through the oxide and are grabbed by oxygen. So you wind up with a positive charge on one side of the oxide, a negative charge on the other, and that's what gives rise to a very high electric field. These fields are on the order of 1,000,000 volts per centimeter. And this is the force that drives the positive and negative ions through the oxide and drives the growth and reformation of the oxide when it's disrupted. We've known since about the 1930s that the currents associated with reforming oxides, repassivating oxides, vary according to this equation, which was developed by Gunther Schultz and Betz. And it shows that the current varies with the thickness of the oxide in this e to the 1 over x behavior. I plot that function over here on the bottom right to show you how steeply falling the current is as the film gets thicker. And in fact, it essentially falls to 0 very rapidly at a limiting thickness of the oxide film. And so basically, when these oxides are disrupted, they regrow to a specific thickness that depends on essentially the nature of this equation. Let me just show you, for instance, here is an atomic force microscope animation of a titanium oxide film in solution as we start at -1 volt and increase the voltage up to +1 volt, driving the growth of that oxide film. And you can see that the dome-shaped nature of the oxide coarsens and thickens over the time of that experiment. So again, this oxide film growth is driven by the electric field and also the tunneling currents to get the electrons out to the outer surface. And as the film grows, you can see that the slope of that line gets less, and so the field falls away until you reach some limiting thickness where the growth essentially stops. So you could take this equation and put in limiting current and limiting thickness where that film will essentially stop growing, rearrange that, and note that the terms out in front of the voltage terms are essentially constants. If I lump them together as M, you can see that the thickness of the oxide depends on this constant M and how far the voltage is away from some onset potential, the passivating potential. And so we would expect from this that the thickness of an oxide film will vary linearly with the voltage applied across that surface. We can also look at cobalt-chromium alloys with atomic force microscope methods, electrochemical AFM methods. And again, just to show you the nature of the oxide films, I have a series of AFM images running around the right side from -1 volt up to -50 millivolts. And if you look carefully between -500 and -550, you can see a distinct change in the scratches here that are on that metal surface. And as you keep going up, those scratches fill in. That's the oxide showing up and growing and filling in by -50. Those scratches are almost completely filled in. And then if you go back to the bottom, starting at +300 and going onward, you can see how that oxide film suddenly changes its topography, its morphology. And then as we get up into the 400 and higher range, you begin to see this active corrosion taking place. That's corresponding to how the resistance of that oxide film varies with voltage. So this rising impedance corresponds with how the oxide film first starts and increases its thickness, and then begins to fall down again as that oxide transitions into this plus 300 and higher range. And so this correlation between the oxide film morphology and its properties is very, very good and indicates the behavior of cobalt chromium across the range of voltages in phosphate buffered saline. Now, going back to mechanically assisted corrosion in oxide films, what we basically experience here is some hard contacting asperity inducing fracture and driving abrasion of the oxide. You could also have edges generated by dislocations where you disrupt the oxide, and the repassivation reaction happens immediately following, right behind that, and you can get oxide debris formed as well as release ions, generate hydrogen, and all of the other myriad factors that we know go into mechanically assisted corrosion. In the single asperity example of mechanically assisted corrosion, we can do more contact mechanics analyses to better understand the interaction. So work we did in the late 90s, early 2000s used high-speed single asperity scratch tests with a diamond tip. You can see a damaged scratch that was induced by one of these tips. And we can measure very accurately the area of that abrasion, the diameter, the length, and understand something about the area abraded as it relates to the hardness of this alloy and to the force applied to that indenter. And indeed, one of the things to note is that the area of contact is really driven mostly by the load applied divided by the hardness. And so when you take that idea and think about the radius of that contact, assuming a spherical contacting radius or contacting geometry, you can get a very nice measure of the radius of contact. When we utilize values for the diamond stylus, the modulus of titanium, and all of the other parameters here, we calculate that radius to be about 5.5 microns, which is really pretty close to that 12 or 13 microns that we're measuring directly from the measurement. And so it looks like single asperity-wise, we can use these concepts of contact mechanics and hard-on-hard contact mechanics to understand the area abraded. Also, with the single asperity, we can look at the details of the repassivation reaction using a model that John Ambrose developed in the 80s that had two parts. One is the oxide forming, and the other is the ions generated. We know from measurement that this current response is somewhat exponential in a decaying fashion, and so we can solve that differential equation and learn about the charge associated with a single asperity scratch and how it's related to the volume of oxide that is reformed as a result of that charge. And so this model is very helpful and in fact shows us the behavior of titanium and cobalt chromium as a function of voltage. And in fact, what we see is, as predicted, the currents are linear with voltage, as I showed you earlier from the high field growth model. And when you put in the known values for these parameters that you either measure or come from the literature, you get the line that overlays that data. And so that's not a curve fit, that's simply putting in the values of the density of the oxide and so on, and you get that curve. So a very good fit between the theory of high film growth and the measured behavior in a single asperity scratch test. The onset potential for titanium is down here at -1 volt. The onset potential for cobalt chromium abrasion is at -500 millivolts. And so those are the important parameters that come out from these tests. When you go to a multiple asperity test, you can see now if you have two surfaces in contact, you can have two areas or multiple areas making contact, but that will be much less than the nominal area. Again, the area of contact will be given by the ratio of the force across the surface and the hardness of the surfaces that are engaging. From that, you can come up with some estimates of the area abraded and make an estimate of the currents that are generated. And these currents are, again, right in line with the currents that we measure for these kinds of contacting interfaces. Additionally, we've taken it a step further, and Vishwa Swaminathan and I, back in 2012, published a paper in Biomaterials that took a pin-on-disc geometry and thought about the asperity-like contact that goes on, and essentially made the assumption that whatever abraded area there is per unit time, that you're going to have film forming currents or a volume of film reform that is equal to that. In other words, as the volume abrades, you are reforming it very rapidly right behind there. The consequence of this assumption is that you can then calculate the film-based currents, again, from parameters that can be measured directly from the experiment or are from literature values. So we have a tool to tell us how much current we should expect from so much area abraded of a surface, depending on the size of the abrasion and the abrasion rate, d delta dt. And again, it's important to note that there are these recurring parameters, rho nf over molecular weight. This is a sort of a Faraday-like constant, which tells you how much charge in coulombs is associated with a volume of oxide formed. And this is very useful for us to make estimates based on the currents that we measure of how much oxidation has taken place. And because, again, we have this ability to control or measure most of these parameters, we can be very quantitative in these kinds of measurements. So some of the results from our pin-on-disc tests have shown us that there is work done during a pin-on-disc fretting corrosion test where we're sliding back and forth and developing a frictional force over a sliding distance. As you raise the normal force in this pin-on-disc test, the sliding distance gets less because of the compliance of the system. And also, there is an energy dissipated, which is the work or the hysteresis energy within each of these curves, and that varies with the amount of load applied. As you get to very high normal loads, you essentially pin the pin on the disc, and it cannot slide, and you just get an elastic-like response. And the corresponding fretting currents that you obtain from such a test are shown here, where they correlate very well with the work of fretting. In other words, the more work done, the greater the amount of current generated, and as that work diminishes, as you get more sticking of the interface, you get less fretting. This also points out that there are conditions where high contact stresses will suppress fretting and will essentially shut down the fretting corrosion reaction. Also shown in this plot are the three materials, titanium, titanium, cobalt, chrome, and the mix, showing the fretting currents and their variation with the contact stress. And you can see each is very different from the other, with the mixed alloy actually giving the lowest fretting corrosion currents of the three different possibilities. When you look at the voltage-dependent effect of these pin-on-disc measurements, I would just want to point out on these curves that you see the same kind of linear dependence of the fretting currents with potential that you saw in the single asperity scratch test. So again, the voltage of the interface or across the interface is very important for the behavior of this system. In addition, the frictional interactions of the interface can be highly dependent on that potential as well, as is shown here. Now, one thing that's new that we are working on is that there is this direct link between the rate of volume abraded and repassivation and the current that is generated as a result of that repassivation. So this approach, this mathematical approach, is essentially a Boltzmann superposition approach. It utilizes something called a Duhamel integral, and what it can do for you is predict the current over time when you have some arbitrary voltage disrupted, or volume disrupted over time. And so just to give you an example of how this works, for a pin-on-disc test, we might have sliding abrasion that looks something like this, where we slide and pause, reverse the slide and pause, slide again and pause, and then the velocity associated with that, the dv dt, is shown here. And then the currents that we measure from that experiment during a pin-on-disc test are at the bottom. But when we take the sliding data and numerically integrate them in this function, this heredity integral, we get this plot of the predicted currents based on this sliding profile, this sliding velocity profile. And you'll notice the similarity both in terms of the magnitudes of the currents generated and the phase and the periodicity of the currents. All of it seems to line up very well. So we have a tool here that can essentially predict for us using, again, either set variables known from the literature or measured in the experiment, like the sliding speed, to make direct predictions of what we would expect from fretting corrosion. So just to emphasize, the charge per cation is important, or charge per unit volume is important, and you can use this term to make estimates of how much volume of material would be lost from a metal surface or how much oxide is formed. So 1 microamp over 1 year will give you about 1.5 millimeters cubed of TiO2 and about 1.75 millimeters cubed of chromium cobalt chrome oxide. Now I want to shift gears for the last few minutes of our talk to focus on the biological interactions with the fretting corrosion or tribocorrosion processes. So the first one is I want to focus on reduction reactions. Then I want to talk about respiratory burst and inflammation and its effects on corrosion. And then I want to show some evidence of how we know inflammatory cells can induce corrosion on alloys, and then present this new paradigm. So firstly, we've been studying since the late 90s, early 2000s, the idea that when you apply a cathodic voltage, when you drive reduction reactions, you can kill cells on surfaces rapidly. So when the surface becomes minus 600 millivolts, you can see cell death on cells grown on that surface in as short as about 2 to 4 hours. The more negative that potential, the faster that reaction takes place. This curve in the upper right shows that when you have abrasion of a metal surface in physiological environments, you can easily have the voltage drop within this range where the viability of cells on that surface can fall away, and you can induce cellular apoptosis, mostly because of the release of these reactive oxygen intermediates I mentioned earlier. We've seen this now both on commercially pure titanium, where below minus 300 millivolts, we go from viable to pretty much all dead cells cultured on these metals. Similarly, with cobalt chromium, there is an electrochemical zone of viability that ranges from about minus 350 millivolts to about plus 300 millivolts. And outside of that zone, cells cultured on those cobalt chrome surfaces undergo rapid cell death, either by apoptosis in one case or necrosis on the other. Now, the currents needed to drive that killing are only in about the 1 microamp range, and so it's not a very high reduction current necessary to kill these cells on these surfaces. These videos that I'm showing are just demonstrating this phenomenon for the minus 400 case, cells at open circuit, and cells at 500 millivolts. What you're seeing is videos that were generated by first creating fluorescent cells that fluoresce their focal adhesion sites, and then monitoring how those focal adhesion sites vary over time as we apply these different electrochemical conditions. So very clearly the cells under cathodic potentials where you might go from a fretting corrosion reaction undergo rapid cell death. Also, when you get above 500 millivolts on that surface, you will induce cells to die via a necrosis pathway. They just basically stop functioning and die. And in this intermediate zone, they remain viable. Now, I want to finally move to this respiratory burst effect, this idea that cells can generate conditions that might exacerbate corrosion. So inflammatory cells engage in respiratory burst, and what will happen is a phagocytic cell will take oxygen, and through this NADPH oxidase molecule in the cell membrane, simultaneously oxidize NADPH and reduce oxygen to a superoxide anion. This superoxide can then undergo various transitions that are shown here, and in particular I want to focus on hydrogen peroxide, hydroxyl radicals, and hypochlorous acid. These species are extremely reactive. They're highly oxidizing molecules, and they are generated and present in both neutrophils and macrophages. Indeed, most of the phagocytic cells of the body utilize these mechanisms to create the conditions to kill the bacterial invader or to go after the foreign body. And so the question is, what role do these molecules play in the corrosion of cobalt, chromium, and titanium alloys? Well, in terms of hydrogen peroxide and pH on cobalt, chromium, we see that with increasing concentrations of hydrogen peroxide from 0 to 30 millimolar, we get a very profound shift in the corrosion behavior of cobalt chromium, where the corrosion currents rise about 40 times just by the presence of these reactive oxygen species up to about 30 millimolars. Indeed, at 5 millimolar, we're seeing as much of an effect as at 30 millimolar. Interestingly, when you go to a lower pH, so this black line on the right curve represents pH 7.4, and when we adjust the pH down to pH 3, we are suppressing the corrosion in the presence of hydrogen peroxide. So acidified hydrogen peroxide containing solutions are not as severe on cobalt chromium as pH 7.4 hydrogen peroxide solutions. So physiological pHs can induce much more significant corrosion of these alloys when ROS species are present. Most recently, we've been looking at the role of hypochlorous acid. My PhD student, Yangping Liu, has noted in the literature that people have measured as high as 100 millimolar hypochlorous acid levels in certain circumstances of inflammation. And when you subject cobalt chromium molybdenum to those conditions, this red line shows up. That is, the open circuit potential for cobalt chromium rises to almost 900 millivolts. And the corrosion current is up here about 3 orders of magnitude higher, about 1,000 times higher than when in phosphate buffer. The resistance of the oxide films of cobalt chromium in the presence of this 100 millimolar hypochlorous acid is down about 3 to 4 orders of magnitude. So a dramatic decrease in the resistance of the oxide. Clearly, the presence of this species in the solution is damaging the oxide film, raising the oxidation potential, and moving the alloy up into a very severely corroding condition. What we think is the consequence of those biochemical species that are generated by inflammatory cells is direct attack of the implant alloy surface. And we began to see in implant retrievals characteristic appearance of cell-like processes on cobalt chromium molybdenum alloy surfaces, which demonstrated corrosion attack of that surface. So these are migrating phagocytic cells, and the dark concentric rings are these regions where you see a ruffled border-like appearance of corrosion damage of the alloy itself. This is not a deposition on the surface, but this corroded region is lower than this uncorroded region out here. In addition, migrating inflammatory cells will leave behind these streaks, which under high magnification look like weld lines. And they are principally made of iron, so we believe iron is the important element driving a so-called Fenton reaction and also inducing this corrosion attack of the cobalt chromium. Some examples of this corrosion attack, both in digital optical micrographs and scanning electron micrographs, show the complex nature of the attack, where there may well be dissolution and re-deposition of ions, as well as dissolution overall on that surface. So these cells are so reactive they are attacking the metal surface. Again, showing you some examples of what we believe are migrating phagocytic cells inducing these damage modes and these iron streaks that are left behind. Also, we've seen examples on bearing surfaces where you see selective pitting going on and evidence of remnant biological species, perhaps biological cells, that have caused this pitting attack, where the pits are actually moving across carbides and other parts of the alloy itself and creating the conditions where corrosion of that substrate can occur. And these are just some other examples. More recently, we've seen actually evidence of attack on titanium 6-aluminum-4 vanadium as well, where very similar biological features appear as corrosion damage of a titanium 6-4 alloy acetabular shell. And indeed, we see some evidence of ingress of these inflammatory cells into taper junctions. And I'll just show an example here, where in digital optical microscopy, we see this very low magnification montage that's been magnified in this region to show these features, and then magnified again to show this is a cell-induced corrosion process Similarly, in the mid region of this modular junction, if you zoom in, you see those 3 dots there, and then zoom in a little bit more, you see those. That's a characteristic pattern of cell-induced corrosion as well. So these phagocytic cells can migrate into modular tapers, and we've seen multiple cases, evidence of multiple cases of these cell-like biological remnants inside these modular taper junctions, driving corrosion of that cobalt, chromium, and titanium surface. And so just to show an example, we have the neutrophil in TEM here, and corrosion patterns on cobalt, chromium, and I believe this is titanium. And the nature of this pattern is very reflective of the organelle structure of the neutrophil in this case, where these granulocytes and other phagosomes appear to be leaving this imprinted pattern, and these larger, perhaps DNA structures are influencing this morphology here. And so we think that we have pretty strong evidence that the damage we're seeing is a direct result of cell attack on these surfaces. And so this basically brings us to this new paradigm where it had been thought really that debris and ions coming from the implant drive a cellular response off in the tissue. However, now it appears that the tissue, the phagocytic cells, can drive corrosion directly, and so we have a feedback system that can operate independently. We could have debris from the device inducing the cells and setting this up, and in fact the phagocytes can get into and alter and influence the taper junctions, the bearing surfaces, which then may modify the mechanical assisted corrosion processes. And so essentially what I want you to remember is it is no longer a one-way arrow of implant causes or implant debris and corrosion causes biology, but that biology can also influence and affect corrosion on the device. And so I'm going to jump over this because I know I'm running out of time, and just want to emphasize that we have shown that these phagocytic cells appear to be influencing the surface of the implant, that it raises the question of patient population and stimulating factors, immune response, immune reactivity effects on whether or not this arises, and that we should not be thinking of tribocorrosion only, but the bio-tribocorrosion aspects of this complex interaction. And so with that, I'll summarize by saying that corrosion is both oxidation and reduction, that these passive oxide films are very dynamic and they're voltage and solution dependent, that we can model oxide film disruption and repassivation with some very accurate mathematical tools and engineering analysis tools that rely on the high field growth model for oxide films, and that finally both reduction reactions and inflammatory species that are generated by inflammatory cells can dramatically alter the nature of corrosion on these implant surfaces. And that finally we have this new paradigm of interaction that we need to consider when we design and build these medical devices and use these alloys. And with that, I will end my presentation, acknowledging those who have supported the work, as well as collaborators, students, and postdocs that did most of this work. And with that, I will open it to questions.
Thank you very much, Dr. Gilbert, for a very interesting talk on the interaction of corrosion, tribology, and biology in orthopedic implants. The webinar is now open to questions. A reminder, if you have any questions, please type them into the questions box in the menu located on the right side of your screen. We have a few questions already. So the first question for you, Dr. Gilbert, is it possible that the damage observed in retrieved samples, such as the ones on the SEM images on the slide entitled ICI corrosion, was due to contact with a bovie?
No, it's really not likely and not possible. That these features, it's very clear when you see damage that's from a mechanical nature where the deformation pattern on the surface will be evident. These are not deformation-based patterns that are arising. And they're far too fine and on a biological scale than they would be from some surgical iatrogenic source.
Okay, so the next question, can you comment on crevice corrosion and crevice created by cell adhesion?
Oh, well, that's a good question. So crevice corrosion, the mechanically assisted corrosion model that I've described does have an element of crevice corrosion associated with it in the modular tapers. And indeed, elements of the mechanically assisted crevice corrosion model rely on the fact that, that crevices can alter the solution chemistry dramatically and also create voltage conditions that are not conducive for maintaining the oxide film stability. The chemical changes that can occur include lowering the pH, increasing the chloride concentration, and depleting oxygen from the environment. Now, I should point out that oxide films don't rely on the oxygen in the solution to reform. They rely on the water to reform. So as long as there is water in the solution, there's still a possibility of oxide reforming. However, under very negative potentials that can arise from the abrasion, you would suppress, or you might drop to or below that passivating potential, and you won't see the passive films reform, in which case you can have a crevice corrosion continue even in the absence of mechanical disruption factors. And we have seen that in several cases of in vitro laboratory testing where we have driven fretting corrosion and then ceased the mechanical loading, and we've seen an ongoing current that was associated with that crevice-like behavior. And just to talk about the cells for a minute, clearly when cells are attached to, migrating on and attached to implant surfaces, they do create an isolated environment. The cell will sort of create a seal around its perimeter to have greater effect and impact of releasing its phagocytic chemistry into that space. So the chemistry of the volume immediately under the cell during oxidative burst will be dramatically different than the exterior solution. On top of that, however, if you have a very prolific inflammatory response and multiple cells basically generating oxidative burst or respiratory burst reactions, you can also change the chemistry of the overall joint fluid to make it more reactive and induce a more generalized corrosion attack of the entire surface.
Okay, so next question, where does the iron come from?
Really good question. So iron is present in synovial tissue. It's sequestered there by synovial sites in proteins called ferritins. You can also have it there as a consequence of any hemorrhaging that might have gone on, any localized bleeding. In fact, there are some patients, I understand from the literature, that have an excess sequestering of iron in their synovial tissues. These can include patient populations that have hemochromatosis, hemophilia, rheumatoid arthritis, but even just generally, the body sequesters iron in these ferritins, these proteins, and indeed, when oxidative burst occurs, one of the effects of hydrogen peroxide is to drive release of the iron from the ferritin to amplify the oxidative effect of that oxidative burst process. And so they're there, they're waiting, and they participate in the inflammatory response when that gets turned up, spun up.
Great. So the next question says, how deeply does the increase in ROS affect the adjacent bone? Do osteocytes apoptosis and contribute to the resorptive loosening process?
Yeah, so that's a really interesting question. There is certainly evidence that oxidative stress can be induced in adjacent tissues by the presence of these species. So you can induce apoptosis and necrosis by high levels of reactive oxygen species. So it is potentially a model to pursue to look at the so-called pseudotumors or local adverse local tissue reactions to be driven not so much by the ions per se, but perhaps by the oxidative burst molecules that are being generated, or indeed by a combination of the two where not only iron serves as a Fenton reaction catalyst, but cobalt and chromium ions can also serve as such a catalyst. So creating much higher concentrations of hydroxide radicals, for instance, in the presence of these cations. So I think it's really maybe a combination of the presence of high levels of ions and these oxidative burst byproducts that are reactive oxygen species that can lead to damage of the soft tissue and perhaps damage of the bone as well.
Okay, next question. To what extent do you think corrosion at the head neck taper is due to cell-induced corrosion and not regular MAC? For example, 1% to 10% or more.
Well, I think the premise of the question may be a little off. I think it's mechanically assisted corrosion is a mechanism that is ongoing whenever you have abrasion of oxide films in the presence of a electrolyte of this sort. So, you know, as long as there are those conditions to lead to mechanically assisted corrosion, it will occur. And then the inflammatory cells can also induce corrosion. So you can have either happening in isolation or you can have them happening in combination. And I think it is such a coupled interaction that it's very difficult to separate out which is which. Now, it may be that we have high levels of mechanically assisted corrosion, which tends to be observed in implant retrievals, but relatively low percentages of revisions associated with, say, trunnion corrosion type symptoms. And so really it raises the question, what's the major driver of the need to revise the implant? It may be we have lots of mechanically assisted corrosion, but it may also be that it's only in those patients that are highly reactive and that begin to have this inflammatory response that are the principal ones to fail. But all of that is very speculative, and we have a lot of work yet to do to best understand the interplay between the biological elements of corrosion and the mechanical or tribo elements of corrosion.
Okay, so we're going to go over a few minutes just to answer the last few questions on our list here. The next question says, is there a good in vitro model to replicate the cellular-based pitting corrosion on cobalt chromium or Ti-6-4 material?
Well, so it's only been, about a year and a half, maybe 2 years since we first documented this, and we've been working in our laboratory to try to develop such a model. I know others around the world are similarly engaged in such an effort, so those efforts are ongoing. I don't believe anybody has shown up yet with a definitive model. I would point out, however, that there is a group in Australia. They have 2 publications out that I've seen. Kadosh is the lead author, I believe, and in there they showed inducing, I believe it was osteoclasts, in vitro to cause corrosion of stainless steel and titanium. And so I think there is some beginning evidence in vitro to document the phenomena that we're describing. There is, I should point out also that there was just recently a paper published from another group confirming the observations that we've made on retrieved implants of the inflammatory cell-induced corrosion that just came out.
Okay, so next question, how do metal ions cause cell necrosis? How is necrosis different from apoptosis?
That's a good question. As a metallurgist, I'll do my best to answer it. So necrosis is just essentially cell death. It's just the cells are dying, and they're dying by, in the case of the positive voltage, they're dying as a result of cations coming off of the cobalt chrome surface. I should point out that when we were at 500 millivolts on titanium, we didn't see cell death. So it's due to the ions, and those ions at that voltage have chromium +6 associated with them. And so that chromium valence ion is well known to be able to penetrate cell membranes, to get into the nuclear core of the cell, and to disrupt the DNA And essentially it does that by the chrome 6 reducing to chrome 3 intracellularly and subsequently oxidizing the DNA. So you're basically breaking up DNA and damaging it by necrosis. In apoptosis, we believe that we're generating these reactive oxygen intermediates, and those are signaling molecules that tell the cell to engage in programmed cell death. So this is a process where the cell believes it is now no longer needed, and it undergoes a series of genetic changes that drives it into a self-killing or a cell suicide type of process. The morphology, how it balls up and fragments in that way, is very characteristic of apoptosis.
Great. So next question, does infection and the presence of bacterial biofilms contribute to cellular-driven corrosion?
So one of the examples I showed of the titanium shell that was corroded was a case that came from an undiagnosed infection. That is, when we looked at the implant in the microscope, you could see the presence of bacterial biofilm. We could identify those bacteria morphologically to look like Staphylococcus, I believe it was Staph type infection. And so, yes, I think it is absolutely possible that in the inflammatory cell response to an infection, it could get to a circumstance where it would induce corrosion of the implant as well.
Okay, next question. Is this ICI corrosion a new phenomenon, or has it existed for decades?
So we have looked at, in our original paper that described this phenomenon, we looked at implants that went back at least 15 years, I think perhaps even as much as 20 years, and we were able to document evidence of it even back then. And so I don't believe it is a new phenomenon. I believe it has been going on, but perhaps it has not been documented because we weren't looking for it. Nobody sort of had the idea that this might occur, and so you don't find what you're not looking for. I guess would be my answer to that question. And it may also be that there have been designs and changes in bearing couples and other things that may have made its prevalence much higher more recently than what we saw back 15 or 20 or 25 years ago.
Okay, second to last question. Is there any correlation between implant infections and cellular-based corrosion of metal implants?
Yeah, so we have not been able to do that study to look at retrieved implants with infection and try to correlate inflammatory cell-induced corrosion with the infections. I would venture to say that it's quite possible. I do know that this recent paper that came out confirming ICI corrosion in a separate retrieval program, they did note that there was a correlation between the presence of adverse local tissue reaction and the presence of inflammatory cell-induced corrosion in the pool of retrievals that they investigated. And so I think there is a pretty good indicator that the severity of the patient's reaction correlates with the presence of this type of corrosion.
Okay, so the last question for this webinar, with regard to cell apoptosis under cathotic potential, is it possible cells die due to large pH increases?
Oh, it's certainly it's possible that it's oxygen depletion, it's possible that it's pH increase, and it's possible that it's these reactive oxygen intermediates. I think there have been studies that have looked at pH shifts. We've done some related to magnesium, and you can get pH shifts that are up into the 8s, maybe high 8s, maybe even low 9s, and cells will still remain viable over 2 hours, whereas under these electrochemical conditions, the cells die rapidly. Again, I haven't done the calculation to estimate the pH at that surface, but I don't believe it would rise to that level in these solutions. So we don't believe it is a pH per se. Additionally, in our first paper out about oxygen levels, we noted a depletion of oxygen at the surface when the voltages got to about minus 800, minus 700 millivolts, whereas we're seeing these cells undergo a very distinct, almost a step function decline in viability below minus 400 millivolts. It's like a switch gets turned on. If you're at minus 350 millivolts, all the cells live. If you're at minus 400 millivolts, they all die. And so there's some trigger that's going on there, and right now our best hypothesis is that we are generating reactive oxygen intermediates, that some amount of them show up that are sufficient at a sufficient rate to induce apoptosis.
Great, thank you. So Dr. Gilbert, I'm going to ask if you can advance one slide so that everybody can just have a chance to check out the references that you've quoted for all of your slides. And with that, we are going to close the webinar. This webinar will be uploaded to the ORS website in the coming week. You will be notified via email when the recording is available. On the website, you will also find information about other resources and programming from the Industry Engagement Committee. Lastly, upon exiting the webinar, you will be asked to complete a short survey. Please complete the evaluation and make any suggestions on how we can improve moving forward. Your input is greatly appreciated. Thank you, everyone, in advance for completing the survey and for joining us today. And a special thank you to our speaker, Dr. Jeremy Gilbert. We look forward to seeing everyone in Disney for the 2016 annual meeting. And this concludes the ORS webinar, New Concepts of the Interaction of Corrosion, Tribology, and Biology in Orthopedic Implants.